Hello, Dan Nedelkovsky here from howtomechatronics.com. In this tutorial, we will learn how to control a stepper motor using the A4988 stepper driver. The A4988 is a micro-stepping driver for controlling bipolar stepper motors, which has built-in translator for easy operation. This means that we can control the stepper motor with just two pins from our controller, or one for controlling the rotation direction and the other for controlling the steps. The driver provides 5 different step resolutions: full step, quarter step, 8 step and 16 step. Also, it has a potentiometer for adjusting the current output, over temperature thermal shutdown and crossover current protection. Its operating voltage is from 3 to 5.5 volts and the maximum current per phase is 2 amps if good additional cooling is provided, or 1 amp continuous current per phase without heatsink or cooling. Now let's close look at the pinout of the driver and hook it up with the stepper motor and the controller. So we will start with the two pins on the bottom side for powering the driver, the VDD and ground pins that we need to connect them to a power supply of 3 to 5.5 volts, and in our case that will be our controller, the Arduino board, which will provide that 5 volts. The following 4 pins are for connecting the motor. The 1A and 1B pins will be connected to one coil of the motor, and the 2A and 2B pins will be connected to the other coil of the motor. For powering the motor, we use the next two pins, ground and V mode, that we need to connect them to power supply from 8 to 35 volts, and also we need to use a decoupling capacitor with at least 47 microfarads for protecting the driver board from voltage spikes. The next two pins, step and direction, are the pins that we actually use for controlling the motor movements. The direction pin controls the rotation direction of the motor, and we need to connect it to one of the digital pins on our controller, or in our case I will connect it to the pin number 4 on my Arduino board. With the step pin, we control the micro steps of the motor, and with each pulse sent to this pin, the motor moves one step. So that means that we don't need any complex programming, phase sequence tables, frequency control lines or so on, because the built-in translator of the A4988 driver takes care of everything. Here we also need to mention that these two pins are not pulled to any voltage internally, so we should not leave them floating in our program. Next is the sleep pin, and a logic low puts the board in a sleep mode for minimizing power consumption when the motor is not in use. Next, the reset pin sets the translator to a predefined home state. This home state or home microstep position can be seen from these figures from the A4988 datasheet. So these are the initial positions from where the motor starts, and they are different depending on the microstep resolution. If the input state to this pin is a logic low, all the step inputs will be ignored. The reset pin is a floating pin, so if we don't have intention of controlling it with our program, we need to connect it to the sleep pin in order to bring it high and enable the board. The next 3 pins, MS1, MS2 and MS3, are for selecting one of the 5 step resolutions according to the following truth table. These pins have internal pull-down resistors, so if we leave them disconnected, the board will operate in full step mode. The last one, the enable pin, is used for turning on or off the fed outputs, so a logic high will keep the outputs disabled. Okay, so here's the complete circuit schematic. I will use the driver in full step mode, so I will leave the 3 MS pins disconnected and just connect the direction and the step pins of the driver to the pins number 3 and 4 on the Arduino board, and as well the ground and the 5 volts pin for powering the board. Also, I will use a 100 microfarads capacitor for decoupling and 12 volts 1.5 amps adapter for powering the motor. I will use an NEMA 17 bipolar stepper motor, and its wires A and C will be connected to the pins 1A and 1B, and the B and D wires to the pins 2A and 2B. But before we connect the motor, we should adjust the current limit of the driver so that we are sure that the current is within the current limit of the motor. We can do that by adjusting the reference voltage using the potentiometer on the board and considering this equation. The current limit equals Vref, or the reference voltage times 2. However, this equation is not always correct, as there are many different manufacturers of the A4988 driver. Here's a demonstration of my case. I adjusted the potentiometer and measured 0.6 volts reference voltage. So the current limit should be that value of 0.6 times 2 equals 1.2 amps. Now, because I'm using the driver in full step mode, and according to the A4988 datasheet, in this mode the winding current could reach only 70% of the current limit. The 1.2 amps times 0.7 would equal 0.84 amps. In order to check this, I uploaded a simple code that sends continuous logic high to the step signal so that we can better notice the current, and connected my meter in series with one winding of the motor and powered it up. What I got was 0.5 amps, which means that the equation wasn't correct for my case. Anyway, now we can continue and make a simple code that will put the motor in motion. Here's the example code. First, we have to define the step and the direction pins. In our case, they are the pins number 3 and 4 on the Arduino board, and they are named step pin and dir pin. And also in the setup section, we have to define them as an outputs. In the loop section, first we will set the direction pin on a high state that will enable the motor to move in a particular direction. Now, using this for loop, we will make the motor make a full cycle rotation. As the driver is set on a full step mode and our stepper motor has a 1.8 degrees step angle or 200 steps, we need to send 200 pulses into the step pin to make one full cycle rotation. So the for loop will have 200 iterations, and each time it will set the step pin on high and then a low state for making the pulses. Between each digital write, we need to add some delay, from which the speed of the motor actually depends. After this full cycle rotation, we will make a 1 second delay, then change the direction of rotation by setting the dir pin on a low state, and now make 2 full cycle rotations with this loop of 400 iterations. At the end, there is 1 more second delay, and now let's upload the code and see how it will work. I made one more example for this tutorial where I control the speed of the motor using a potentiometer. You can find the source code of this example on my official website. That's all.